Hello everyone. In this video we're going to get an overview of the things that we need for section 4a and 4c. So essentially we're still working on defining the sinusoidal functions, right? So we have a function that is y equals z plus a sine of v x minus c, right? This is the most general sinusoidal function. We have that this is the midline. We have that this is the amplitude. And we've been working with this b, which is this b is like the speed of the wave and is related with the period. So b is in terms of 2 pi over the period, right? And this is what we call the speed of the wave. There are a couple of relationships that are tied to this. Of course, the period, and the period can be computed backwards, so 2 pi over b. And there's going to be the frequency of the wave. And the frequency of the wave is how much it will take in terms of making a full turn to the unit circle. And the frequency can be considered as 1 over the period. So these are quantities that are going to come into play in what we're going to do on 4a and 4c. And of course, the last one will be c, which is the horizontal sheaf. And so let's see a little bit using the Desmos calculator. Let's see what happens when we are taking a sine function and we're making some of the modifications. So if we have y equals sine of x, this is a regular sine function. But now let's take a look at what happens when I increase the speed. So I'm going to change now to 2x. And so now notice the blue one is much more faster. Before, the red one, it takes 2 pi to complete a full turn. But now notice that if I make this twice, then this is going to complete a full turn twice as fast. So now it completes a full period in pi 0. I can do this faster if I increase the speed. So for example, if I do a 4x, now you can see this is 4 times quicker, and now it only needs pi half to complete a full rotation. Okay, but now I can also make it slower, of course. So if instead I do sine of 1/2 and then of x, notice that now it's going to take twice to complete the full period. So now notice this completes in 2 pi, the original function, the red functions. But now my purple function, it takes 4 pi to actually complete his period. So of course the speed is related to the period. That's something that we already discussed. So it kind of makes sense that you see that the speed is related, the speed of the wave is related to how much it's going to take the sinusoidal function to cover a single period. Now, that is going to be related to what we're going to be doing in 4a. So in 4a, we're going to come back to modeling the pendulum. And in the pendulum, this time, I'm going to give you a function theta of t. And that function theta of t is measuring the angle that the pendulum is making. We're going to have a position theta 0, that is the initial angle that the pendulum has. This is measured in radians. And of course, we have some other things influencing. This time, instead of using a sine function, we're going to use a cosine function. And we're going to have that other factors, like for example g, which is the gravity, the acceleration due to Earth's gravity, and L is going to be the length of the pendulum. t, of course, is going to be the time since releasing the pendulum in seconds. So those are all the parts that are taken into account here. Now, the variable t is not inside of the square root of this. This is the square root only of g over L. So we want to determine the model for the original pendulum. And so, for example, here you see, assume that the initial angle is 0.148. Notice that that is theta 0. And so if you're using that information, and you have theta of t is theta 0 cosine of square root of g over L and then t. And then they tell you, hey, your initial angle is going to be 0.148. So then you can very quickly find out what that function is, and you just replace this value by 0.148. Of course, you already know what the gravity is, and so you can use the value of gravity to fill the rest of the function. So in here, in particular, we have that we're going to approximate the gravity by 9.8. So this will be 9.8. And then later, we're going to use the length of this. We're assuming in this particular case that we have given length of 67 meters, sorry. And so this will be 67 here. And so that's it. This is giving you the function that you're going to be using for plotting here. Notice that this is very similar to what we've been doing. So this is going to reflect the amplitude, and this is going to reflect the speed of the function. So from this, you're going to be able to also find a period. Okay? So there is a discussion here that you need to go through when it says, well, we know that cosine of t has a period of 2 pi. So since we have a different formula here, what value of t will cause you to take the cosine of 2 pi? And so what we mean by that is, well, 2 pi is going to occur at some point where this is going to be 2 pi. And so you need to solve for t to find out when that's going to happen. And notice that if this is really b, so 2 pi over this will be just giving you not only the time here, but that time in particular will be the period. Okay? All right. So once that you do that, then you can get some information about here, and once that you get the information about the period, then you can calculate the frequency. Again, the frequency is going to be in terms of the period, 1 over p, so you should be able to obtain that. And then once that you do that, then let's suppose that we change the initial position. So instead of having theta 0 be 0.148, let's do 0.2. So now your function is going to change. So now you need to change the function, and you need to see how it behaves. You need to say see again what is the period of this new function, and what is the initial position with this. Also, you want to sketch this and make a comparison between the two graphs. So that overall is what you need to do for 4a. So it's nothing new. We're just making a comparison of two graphs with two different amplitudes possibly, and two different and the possibility of changing the period here. So that's what you're gonna be studying for 4a. Now in 4c, what we're gonna do is we're gonna explore what happens if I make a shift. So for now, we're gonna forget about the amplitude and all these different things that we've done before. So we're only gonna go here. And so now the type of modifications that we're gonna make is what happens if, let's say, if I do X, let's say, and I move 1, what happens? And so you can see here the difference with the black one. Essentially, we're moving 1 point away, and this is shifting to the right 1 unit. So this point is now being shifted here 1 unit. And so you can have also certain variations. So for example, you can have 2x minus 1. And then now you can see that there's a variation of the speed as well. And they're asking you to compare what happens if you have like 2x plus 1. And so what's going to happen is that they're both the same. You're not gonna find a very big difference on them with the type of function that it is. So if I remove sine of x, you'll see that they have pretty much the same type of behavior. They probably go with the same period. They're just shifted. This one that is shifted to the right, while the other one is being shifted to the left. So that's the type of comparison that you can make here with this one. Now, in the context that we're going to be using here, we have a motor that has a spinning of 150 revolutions per second, and is measuring the force that a cell phone exerts over the person when it vibrates. So here, this motor force is measured by R of t equals 0.2 sine of 942.5 t plus certain 5, with R of t is the force of the vibration in newtons. So what do we want to do here? What you want to do in here is essentially a comparison of what's happening. So what's happening if I move a certain amount in here. So for example, here we're going to assume that the initial angle of the counterwave is 0, phi is 0. So you want to write this out, and you want to plot what you have here. So you can do this with your calculator, with Desmos, or whatever you want. Then after that, you're going to see what happens when you shift with pi minus pi over 6. So there's not a lot to do. Just do this. You can do this in Desmos if you want to. But the important thing is that you understand what's going on. And it's important to know that the shift here, so for example, if I'm analyzing the shift, notice that what is really happening is that I'm shifting, for example, for this function here, I'm shifting half a unit. I'm not shifting 2. I'm shifting half unit to the right or half unit to the left. Okay, because this part, this 2 multiplying here, is just going to represent the speed of the wave. Okay, so that pretty much accounts for everything that you have to do. I'll be back on Monday to just showcase a little bit of this more. But in the meantime, you can continue working and submit this. I'll make a quick extension until tomorrow, so you have a little bit more of time to work individually. But it's not a lot of particular work in this session. Just identify the concept of the period and how it's located in a particular function, and also the concept of the phase shift.